Okay, let's talk about cyclohexane, very important molecule. So here it is, cyclohexane. And so the first thing we want to notice about it is that all the bond angles are 111. And now that's close enough to 109.5. Remember, these are all sp3 carbons in all of these cycloalkanes that we're talking about. And so what this means is that it has no angle strain. So no angle strain. All the bonds are staggered in cyclohexane. That means we have no torsional strain. And finally, the hydrogens are too small to get too close to each other, just like we saw in molecules like ethane. And so there's no steric strain present in cyclohexane either. So no angle strain, no torsional strain, and no appreciable steric strain, which leads us to conclude that cyclohexane itself is strain-free. So what we saw with a couple of the other molecules is that they had low energy conformations. For example, cyclopentanes was the envelope. So cyclohexane has a number of conformations, but the major lowest energy conformation is called the chair, and that's what we're going to focus on. So there are others that have different names. You can read about those a little bit, I think, in the book, but we're really going to focus in on the chair, and that'll be enough for us. So some ideas about this. First of all, every cyclohexane has two identical chair conformations. So there are going to be two chairs associated with each cyclohexane. Now the second thing is, every carbon on the ring, the bonds that are coming off of the carbon that are not ring bonds, that is the ones making the ring itself, every carbon in the ring has an up bond and a down bond. So let me write that down and then explain what I mean by that. So an up bond and a down bond. Now that up and down is relative to a plane that goes through the ring. So an average plane, an average imaginary plane. If you look at this at the surface that the molecule in the photograph is resting on, imagine a plane that's going through the molecule like this, that's parallel to that surface. So that's the plane that we're talking about. So relative to that plane, a bond at a particular carbon atom can either be up or down. So let's number the carbons in this so that we have some points of reference. So let's say that's number 1. We'll call this carbon 2. Here's 3, 4, 5, and this guy is 6. Okay, so at carbon 1, this red bond is pointing up relative to that plane, and this one is pointing down. At carbon 2, it's this black bond that's pointing up. Oops, I'm sorry, I wrote down what I meant to write up. And this one's pointing down. And it goes that way all around the ring. So this is down, this one's up. The red at 4 is down, the black is up. At 5, black is down, red is up. And then finally at 6, black is up and red is down. So every carbon has a bond that points up relative to an average imaginary plane through the ring, and a bond that points down. Okay, so every cyclohexane has that feature. There's another feature that's very important to talk about with cyclohexane, and that is that each of these bonds has a particular label. So there's 2 labels. So every carbon in the ring has what's called an axial bond and also what we call an equatorial bond. Okay, so let me show you what I mean by that. So look in the photograph to the left, and what you're going to see are those red bonds, and I'd like you to focus on those first. Notice that those go directly up and down. They're perpendicular. They're all perpendicular to the average plane that goes through the ring. Okay, I'm saying average plane because remember the ring is not flat, but they're perpendicular to that average plane. Those are the axial bonds. So in this picture, the red bonds are axial, and the bonds that extend more closely to that average plane are the equatorial bonds. So those are, in this photograph, in this model, the black bonds. Now, if we look at the pattern of the axial and equatorial bonds around the ring, let's start at carbon 1, and notice that the axial bond there is up. If we go to carbon 2, the axial bond at carbon 2 is down. Proceeding to carbon 3, it's axial up. Then at 4, it's axial down. 5 is axial up. And finally 6, the axial bond is down. So the axial bonds alternate up and down around the ring. And as you can imagine, the equatorial bonds are doing exactly the same thing. So at carbon 1, the equatorial bond is down. Carbon 2, it's up. At carbon 3, the down bond is the equatorial one, and so on all the way around the ring. So the axial bonds alternate up and down around the ring. As do the equatorial bonds. Now, by convention, we have a very specific way of drawing the chair. So it's another drawing lesson. So let's take a look at how an organic chemist will properly draw a cyclohexane chair. So you're going to start with two parallel lines drawn like so, and then you're going to connect those lines with two more sets of parallel lines. Like so. It looks like the Budweiser beer symbol. So let's start in the upper right corner. I'm going to make that carbon 1 and then just number clockwise around the ring. Okay, you want to think of this as a template, okay, so that every single cyclohexane that you draw follows this template. The template gives people who are looking at your drawing information about whether a bond is up or down or axial or equatorial. So to convey that information, it has to be drawn in exactly the same way every time. So starting at carbon 1 in this template, let's start drawing the axial bonds. So at carbon 1, here's an axial up bond. At carbon 2, the axial bond would be down. At carbon 3, it's up. At carbon 4, it's down. At carbon 5, it's up. And at carbon 6, it's down. So going around the ring, axial up, axial down, axial up, axial down, up, and down. Notice that the axial bonds are all parallel to each other, just like they are in the photograph up above. Now let's do the equatorial bonds. Now the thing about the equatorial bonds is that they are going to be parallel to a ring bond, that is a bond within the ring itself, that's one bond away from where the equatorial bond is attached. Okay, so let me show you what I mean by that. Let's start at carbon 1 again. Because the up bond at carbon 1 in this template that we're drawing is up, that means the equatorial bond will be down. So it's going to be drawn like this. So this will be equatorial and down. And this bond is going to be parallel to the bonds in the ring that are one bond away from the carbon where that equatorial bond is attached. So it's attached at 1, so if you go out one bond in both directions from carbon 1, the next bond is what this equatorial bond should be parallel to. At carbon 2, the down bond is axial, so the equatorial bond is going to be up. And so this bond will be parallel to these ring bonds. At carbon 3, the equatorial bond is down. So because it needs to be parallel to these ring bonds, it's going to have to point sort of down and to the left. Then we have an equatorial up. And that one, the shading on it or the highlighting, it should be parallel to the 5,6 bond and the 3,2 bond. Our next equatorial bond will be down. And that will be parallel to the green shaded bonds. And then finally, at carbon 6, as I've labeled them, is an equatorial up bond. Okay, so that is, if I do say so myself, a perfectly drawn cyclohexane chair. So you should always draw the chair in exactly the same way every time. It has to comport to this template so that people can understand when they look at it and they look at any of the carbons in the molecule, what you're trying to convey. Is a bond axial? Is it equatorial? Is it up or is it down? Okay, so take a minute and draw a chair of your own off to the side. So take your time, pause the video and draw a chair, and then we'll come back and talk about that chair. Okay, so I've drawn most of the chair, but I've left off 2 of the equatorial bonds because I want to talk to you about them because these are the ones that mess people up. So the first thing is, see these 2 blue highlighted carbons? You want those to be offset from each other the way I have here. If you draw one that's right above the other, then you're not going to be able to show very clearly these axial bonds. So be sure that those are offset from each other. The other thing is to remember that when you draw the equatorial bonds coming off of each of those carbons, that they need to be parallel to these outer ring bonds, which means that this one is going to be pointing this way, and this one will be pointing this way, okay, so that they're all parallel. So that tends to mess people up. They'll draw those equatorial bonds pointing in the wrong direction. That's where you lose points, and so you don't want to do that. So again, you need to follow the template very carefully each time. You can't kind of make up your own rules and draw things like this which is not a cyclohexane chair at all. In fact, one of your former colleagues, a student I had many years ago, referred to this as bow tie pasta with hair. Okay, so bow tie pasta with hair doesn't give you any information about whether a bond is up, down, axial, or equatorial. It's not conveying the information that we need to convey that is conveyed in the template. So practice drawing cyclohexane so that you can do it correctly. Now, cyclohexane, like other molecules, both cyclic and acyclic, is what we call conformationally mobile. That just means that it can adopt different conformations. And of course, it does so the way all molecules do, by rotating around the single bonds within the molecule. So what we're looking at on this page is what's called a chair flip or a ring flip. Okay, now these mean the same thing. It just depends on which book you're looking at, which terminology they're going to use. But people will call these chair flips or ring flips, and you can use those terms completely interchangeably. What this doesn't mean is that we're flipping the molecule over. So this does not mean, the term flip doesn't mean that we're just flipping the molecule over like a pancake. Rather, it's the term to describe the fact that we're rotating around the bonds in the cyclohexane to access the other chair. So we're rotating around the ring bonds to access the other chair conformation. Remember on the previous page, I told you that there were 2 for every cyclohexane. So that's what we're up to here. Okay, when you draw the ring flip, okay, I'm going to show you how to do the ring flip in just a second. But to draw it, typically what you're going to do is change the orientation of the lines. So remember, we started with these 2 sets of parallel lines. So when you draw the ring flip, by convention, you just tilt them at the opposite angle. Now, you don't have to do that. It is conventional, but you can draw a perfectly legitimate and valid structure without doing that. So what I mean is, you could also draw the chair flip just like the original one, except not that badly that I just did. Okay, so let's look at these 2 pictures. On the left is a cyclohexane. Okay, this is actually the molecule that we started with. And what I've done is put a special atom, a hydrogen, an orange hydrogen, on one of the carbons. And so what I'd like you to notice about this is what kind of a bond is that atom attached to? Is it axial? Is it equatorial? Is it up or is it down? Okay, so hopefully what you said was that it is axial and up. When the ring flips, what you get is the new chair to the right in the right photograph. Okay, and notice that the perspective slightly changes. So carbon 1, as I have it labeled in the photo on the left, is exactly the same as the carbon 1 in the photo on the right. And even the orange hydrogen knows that. Okay, now notice what happened. And I'm going to show you this on a video in a second. An axial up bond in the first chair, once we undergo a ring flip, is now what kind of bond? What kind of bond is this? If you said equatorial and up, you'd be correct. So here's the deal. First of all, the 2 chairs are converting because of rotation around all of the carbon-carbon single bonds in the ring. Okay, so there's that. But the other thing is that bonds that are up stay up after the ring flip. So if a bond is up, it's up. It's not going to change to down just because the ring flips. So a bond that's up stays up, and a bond that's down stays down. So up stays up, down stays down. However, axial bonds become equatorial bonds. And equatorial bonds become axial. Okay, so what I'd like to try to show you now, and I hope that this will be successful, I'd like to try to show you how you know that you've made the cyclohexane molecule correctly and how to do the ring flip, and then we're going to see the axial bond becoming an equatorial bond and what we just talked about. So let's take a look at this. Okay, so here's the cyclohexane. So hopefully we can all see this. Okay, so what I'd like you to focus on are the axial bonds. Notice that the axial bonds are all parallel. That's how you know that you've made the model correctly and that it's actually in the chair conformation, is that all the axial bonds will be perfectly parallel to each other. And so if you have a model like this one, I've just kind of tweaked it, and those bonds are not parallel, you just need to do a little adjusting, rotate around the bonds, and get everything so that the axial bonds are parallel. Once you get to that, you know that you're in the right place. Okay, so to do the ring flip, what you're going to do, so here's the molecule, is you're going to hold the molecule in both hands on opposite carbons. So one hand on the first carbon and the other hand on the fourth carbon. Okay, now when you do that and you hold the molecule in front of you like this, what you're going to notice is that one of those carbon atoms is a little bit higher up than the other one. In this case, it's this one that's higher up and this one's a little farther down. Okay, so higher, lower. So what you'll do with the carbon atom that's higher up is you're going to take that and torque it down. And with the one that's lower, you're going to take that and torque it up. Okay, and then just do a little bit of adjustment. Make sure that the axial bonds are now parallel to each other again. And this is what you get. Okay, let's go back in the other direction. So I'm going to go back to the original chair. So in this case, I'm going to pull this one down, pull this one up. Okay, all my axial bonds are parallel, so I'm in good shape. Okay, now let's focus exclusively on this hydrogen here and the bond to it. As of right now, what kind of a bond is that? Is it axial or equatorial? I'm hiding behind the molecule. Okay, so I'm hearing everyone say axial. Very good, it is. Is it up or is it down? You're right, it's up. Okay, so what we would expect then in the ring flip is that this is going to stay up, but it's going to become an equatorial bond. So let's do the ring flip and see if that actually happens. It's like magic. It did happen. Would I lie to you? No. Okay, so now it's an equatorial bond. So that's happening, remember, with all the bonds all the way around the ring. Up stays up in the ring flip, down stays down, but axial bonds become equatorial and equatorial bonds become axial. Let's look at some more drawings. Actually, before we leave this page, here is how you would look at a Newman projection of cyclohexane. So in cyclohexane, notice that you're looking down two bonds at the same time. And so those bonds are the ones that I bolded in the picture. So here and here. And so you can track with the numbers on the chair on the left with the Newman projection on the right. Okay, now we're going to come back to this in a little while when we talk about some other things about cyclohexane, but I wanted to throw this out so you become familiar with the Newman projection for cyclohexane. Let's focus now on the torsion angles in cyclohexane. Now we can use what we learned about the different ways of drawing molecules, including the Newman projection and the Sawhorse projection, to figure this out. So what we're going to do is look at three structures, but they're going to contain the same information. So the first one is the chair. The middle one is the sawhorse. And the one on the right clearly is the Newman projection. Okay, so the bonds that we're going to be considering are the ones that I've made dark. So I'm highlighting them now. So if we take that piece, actually let's put some labels on the ends of these bonds. We're going to call this A. Here's X. We'll call this Y. Here's B. And then this is outside of the pattern, but we're going to label it anyway because we're going to talk about this. There's C. Okay, so if we pull that bolded piece out of the molecule, what we get is a sawhorse. So it looks exactly like a sawhorse. So let's put the labels on. So this carbon here in the chair is this one. And as it turns out, that's going to be the front carbon in the Newman projection. So attached to that carbon, pointing straight down, is B. Going up and to the right is Y. And then the back carbon has A pointing straight up and X pointing off to the right. Now these squiggly lines, here, and then in the Newman projection, here and here, what that means is that those bonds go to another, to the rest of the structure, but that the rest of the structure is not that important for us to show in terms of what we're trying to talk about with what we're looking at here. Okay, so for your Newman projection, again, it's that pink carbon that's the front one, so you're going to be looking this way, which means that in the Newman projection, this is B, this is Y, A is straight up at the top, and X is over here. So we know how to assess these torsion angles from a Newman projection, but the thing that we can do with the patterns that we're going to see is we can extrapolate them to any pair of bonds all the way around the ring. So I pulled out the right side of the molecule just to make it easy to look at. We could have done the left side as well. But the patterns that we're going to see apply to the entire ring. So we'll see how and why in just a second. So let's look at some torsion angles. So let's start by looking at A and Y. Okay, so first of all, I'd like you to look at the bond to A and the bond to Y. What kinds of bonds are those? Are they axial or equatorial? Okay, so let's label these in the chair. The bond to A is axial. The bond to X is equatorial. The bond to B is axial. The bond to Y is equatorial. And so the AY bond, we have an axial bond and an equatorial bond on adjacent carbons. The relationship of A to Y is a 60-degree angle, and so they are gauche. Let's look at A and B. A is an axial bond. B is also an axial bond. They're on adjacent carbons. And as we can see, the torsion angle between A and B is 180 degrees, so they are anti. And then finally, X and Y. X is equatorial. Y is also equatorial. And what we see in the Newman projection is that this is a 60-degree torsion angle, and so X and Y are gauche. Those are all the patterns you need. So if we're looking at pairs of adjacent bonds, okay, so remember when you're assessing a torsion angle, you're looking at a bond on the front carbon and what the angle is between that bond and a bond on the back carbon in your Newman projection. So the bonds have to be coming off of adjacent carbons. So adjacent, in the table we're about to make, means bonds on neighboring or adjacent carbons. Okay, so if you have two bonds coming off of a cyclohexane chair, they're adjacent to each other, and one is axial and one is equatorial, their relationship will always be gauche. If you have two axial bonds that are on adjacent carbons, their relationship will always be anti. And if you have two adjacent equatorial bonds, their relationship will always be gauche. So all of this you can take to the bank. It's never going to be different than this. Okay, now let's go back up to our original chair. And let's try to extrapolate these patterns to some other things. So let's look at two relationships. So B and C. We're looking at those two bonds. Well, first of all, we have to understand what kinds of bonds we're looking at. The bond to B is an axial bond. The bond to C is an equatorial bond. So we have an axial and an equatorial, which means that B and C must be gauche. Now this is important to recognize that the pattern still holds. Even though the way we draw the template, it's kind of hard to see. So we can be certain, though, that the patterns that we saw in the segment that we pulled out and analyzed, those patterns hold all the way around the ring, like I said. Let's look finally at the relationship between C and Y. C is equatorial. Y is also equatorial. When you have two equatorial bonds next to each other like this, their relationship is also gauche. And again, when we look at the template, it's really hard to see that those two are gauche to one another. But we know that because they're adjacent equatorial bonds, they're going to fall in line with the pattern that we developed by looking at the right side of the molecule, and thus they will be gauche.